Now, when we know how to build a Taylor polynomial for a function of one variable, let's consider a Taylor polynomial for a function of two variables. So for a function f from R2 to R, that means we have some function f of two variables. Let's call them x and y. We can build the Taylor polynomial of order 0, which will be again a constant function, and the best constant is the function value at the point x0, y0. x, y are the two independent variables of the function t0, and x0, y0 are two constant values. So this is just a one number. The graph of such a function is a horizontal plane, a plane at this height, parallel to the xy coordinate plane. But then we can do better. Better approximation is t1. And this will be a linear function. The absolute value, the absolute term will be the same because we want to keep the best height at the point x0, y0. And then we want to add some coefficient times x and some coefficient times y. And the best coefficient is the partial derivative of the function f with respect to x at the point x0, y0 times x minus x0 plus the partial derivative of f with respect to y at the point x0, y0 times y minus y0. Up to here, it looks like the Taylor polynomial of order 1 for the function of one variable. And now when we have two independent variables, then this term has a corresponding brother, namely the term with y. And these coefficients are chosen in this way so that the slope in the x direction and in the y direction is the same for t1 and for the function f. Taylor polynomial for the 2 contains these three terms again. So let's call them just t1 plus some quadratic terms. And now there are three quadratic terms: x squared, y squared, and x times y. And we want to multiply this by some coefficient a, this by some coefficient b, and say this by some coefficient c, such that the second derivative of t2 with respect to x is equal to the second derivative of f with respect to x twice. We want to choose b such that t2, when differentiated twice with respect to y, we get the same value as when we differentiate the function f twice with respect to y at the point x0, y0. And we want to choose the constant c such that t2 differentiated with respect to x and then with respect to y is equal to the mixed second derivative of f. Well, this is the similar computation as for the Taylor polynomial for a function of one variable, and it turns out that a should be 1/2 of the second derivative. At the point x0, y0 times x minus x0 squared. This is also simple. This is the same, just instead of x we have y. So we add 1/2 of the second derivative with respect to y at the point x0, y0 times y minus y0 squared. And what about C? Okay, let's derive the value for C. So if we have just this single term, let's call it Cxy. Small t, just that means one piece of the Taylor polynomial. And we want the derivative of t with respect to x and y be equal to this. So small t differentiated with respect to x is c times y, and when differentiated with to y once again is c. And we want this to be the derivative of f. So e is just the derivative of f at the point x0, y0. And now we multiply by x and y, possibly shifted by x0 and y0. So this is the second order Taylor polynomial for a function of two variables. T1 is the absolute term and the two linear terms. And then there are three quadratic terms. One with x squared multiplied by 1/2 of this second derivative. Then with y squared multiplied by 1/2 of this second derivative. And then this mixed term, which is also of order 2, x times y multiplied by this. Alternatively, we can factor out 1/2, and then we multiply by 2, and we can write it this way. Here we add all these terms. Let's consider some exercise for the Taylor polynomial of order 2 in the next session.